Good morning, happy Wednesday. It is May 20th, and today we're going to be starting a new unit on nuclear chemistry. So let's get right into it. Before we begin, I just wanted to point out from last week's acid-base demo, there were about 7 of you who actually did guess the right indicator, which was universal indicator. So a lot of you noted that the purple color at the beginning demonstrated a base, and universal is purple in a base. The Alka-Seltzer tablet kind of neutralized it, bringing it to a greenish yellow. And then when I added the acid, which was the vinegar, it turned red. So universal indicator was the winner, but a lot of you had some good reasoning behind other indicators that you chose. So moving on to this week, topic 12 in your review book is on nuclear chemistry. We're going to spend a few weeks on nuclear chemistry, which is a pretty fascinating and sometimes physicsy subject. So the checklist for this week, we're going to do a really quick daily discovery, which is just a review of the atom. In this video, I'm going to go through the outline, notes, and independent practice, and this will require you to submit something to me this week. We're going to talk about your choice activity, which also requires you to submit something to me this week. And then some feedback was we're kind of sick of quizzes. I know that we kind of like the format, but I'm going to give you a week off from quiz. So my daily discovery question is really just review in disguise. What you see to your right is a carbon atom and the subatomic particles that make up a carbon atom. So I want you to think about this question and answer it to yourself. What makes this carbon atom carbon and not nitrogen or oxygen? So basically we should be thinking about which subatomic particle identifies an element. So we may remember that the atomic number is what classifies an element as carbon or nitrogen or oxygen, but the atomic number applies to the number of protons in the nucleus of an atom. So carbon is carbon because it contains 6 positive protons in the nucleus. The electrons don't define it, and the neutrons don't define an atom. So my next question is, if you wanted to change carbon into another element, would you have to change A, the proton number, B, the neutron number, or C, the electron number? And hopefully we are thinking A, you would have to change the proton number. What we've learned in the past is we can change the neutron number, but that just doesn't create a new atom. It creates what's called a new isotope. When we talk about chemical reactions, we can change the number of electrons, but we're not making new atoms, we're making something called ions. So in nuclear chemistry, we are going to change up the number of protons in the nucleus of atoms to turn one element into new types of elements. Usually this process requires results in the release of a lot of energy, and we'll talk more about nuclear energy in the weeks to come. So before we get into this week's lesson, you need a few things out. So if you don't have these things ready to go, pause the video and grab them. You need your review book open to topic 12, nuclear chemistry. You need access to a reference table of some kind, either your copy, there's one in the appendix of your review book, or you can Google one. And it's recommended that you take notes and try some of the practice problems with me as I go through them. So if you need to grab any of those, pause the video and then come back. We are only going to cover pages 216 to 221 this week. And this is going to cover what it means for a nucleus to be stable, what it means for a nucleus to radioactively decay, how to write nuclear equations, and defining transmutations. Before we begin, you cannot write nuclear equations without understanding isotopes and isotopic notation. An isotope is an atom of the same element that contains the same number of protons but a different number of neutrons, and therefore they have different masses. But since they have the same atomic number of protons, they're still considered the same element. Isotopic notation is seen over here. When you write an isotope, in isotopic notation, you include the element symbol, the mass number on top, which we calculate by protons plus neutrons, and the atomic number on the bottom, which is the number of protons. So when you look at the periodic table, the atomic number goes on the bottom, and then typically with these isotopes, they're going to tell you the mass number right in the question. So I have 3 examples down at the bottom, 3 isotopes of carbon. Carbon 12 means that it's carbon with a mass of 12. So that's the isotope you see here on the page. Mass is 12, carbon is the symbol, and on the periodic table, the atomic number is 6. That's how I would write carbon 12 in isotopic notation. Carbon 13, carbon, it has an atomic number of 6, which is on the bottom. And this tells me the mass of that isotope, 13 on top. Go ahead and write the isotopic notation for carbon 14. And carbon 14 would look like this. It's really important that you know how to write this moving forward. All right, so starting off in the review book, we start off with this graph looking figure 12-1. So while you listen and take notes, you might want to kind of check out this figure. Basically, isotopes can be stable or unstable. The stability refers to whether or not there are too many neutrons, up to double, compared to the number of protons in the nucleus. If there's way more neutrons than protons, that is probably an unstable nucleus. There's just not enough room and attraction for everything to be held in there. If it is unstable, we call it a radioisotope. And typically anything with an atomic number above 83 is going to end up unstable, because if it has 83 protons, chances are it has more than double the amount of neutrons compared to protons. So if we look at the isotopes of carbon, carbon 12 has the same number of protons as neutrons, 6 and 6. So carbon 12 is a really stable isotope. But something like carbon 14, although it doesn't have double the amount of neutrons, it has more neutrons than protons. So carbon 14 is an unstable nucleus, and carbon 14 is actually radioactive. What it means to be radioactive is that there are particles emitted, literally spit out from the nucleus. And when particles are emitted from the nucleus of an atom, we call it radioactive decay. We are going to talk about 3 types of particles that can be naturally spit out, emitted from unstable nuclei. And those 3 particles are called alpha particles, beta particles, and positron particles. So since there's 3 types of particles, we say there are 3 types of radioactive decay. The type of decay is defined as the type of particle emitted from the nucleus of a radioisotope. It's sort of like a fingerprint in a way, because certain types of radioactive elements spit out specific types of particles. So for example, if the nucleus of an unstable atom emits an alpha particle, Greek letter A, is like losing 2 protons and 2 neutrons from the nucleus. So I'm gonna avert your attention here. What is an alpha particle? An alpha particle contains 2 protons and 2 neutrons. So when this particle is spit out of a bigger atom, it actually looks like a helium nucleus. Because of the 2 protons and 2 neutrons, its mass is 4. And the 2 protons gives it an atomic number of 2. So what we want to do is think about what happens when an element loses this from their nucleus. If you lose 2 protons, the atomic number is going to decrease by 2 and you're going to form a new element. The mass number is going to decrease by 4. So what does that mean? Let's take a look at an example. Radium-226 is a radioactive isotope. So this element is unstable because it has an uneven number of protons and neutrons. So what happens is, if it spits this particle out, it creates something new. That something new has a mass number that is 4 lower than the original isotope. So the mass went from 226 to 222. That alone does not change the identity of the element. But if you also lose 2 protons, the new atomic number would be 86. And atomic number 86 is not Ra anymore, it is Rn. It has a new identity. So alpha decay changes one element into another. Another type of decay is beta. Beta particles, B negative, results in what would be, when all said and done, gaining a proton. Beta particles have no mass at all. So the only thing that beta decay is going to change is it's going to increase your atomic number by 1. Carbon-14 that we've been discussing decays by beta decay. So what does that mean? Well, there's no mass change, but the atomic number increases by 1. So instead of carbon-14, we lose the equivalent of gain the equivalent of a proton, and I now become nitrogen-14. And we'll do more examples of this later. Me saying it gains a proton is sort of like 4 steps later. Don't worry about this stuff unless you're headed to AP. The opposite of a beta particle is a positron particle. So if a beta is like saying you're gaining a proton by this process, a beta positive particle, which is called a positron, is like losing a proton. So something like carbon-10, which is a pretty rare isotope, would turn into boron-10 by losing or decreasing the atomic number by 1. So the type of decay is based on what particle gets spit out, and that is specific to the isotope. I know that this can be confusing, but we're going to do some examples. Before we talk about writing these equations, certain types of decay release more amounts of energy than others, and this can be harmful. So gamma rays are a wavelength of energy similar to X-rays that can be emitted alongside these particles that are spit out of radioactive nuclei. It's not a particle itself, it is a wavelength of energy, and it has what we call really high penetrating power, meaning it's harmful when it interacts with living things. It can cause changes in the DNA, which are called mutations, and those mutations can lead to cancer. Gamma radiation is a byproduct of alpha, beta, and positron decay, but in varying amounts. So alpha, beta, and positron decay don't all have the same harm factor, but there's different precautions that need to be taken for all of them, since gamma radiation is harmful to DNA. Figure 12.2, I went back and forth if I wanted to go over this, but I feel like I should, shows what happens when you separate radioactive emissions. And this just has to do with knowing the charges of the particles. So what they have here, and I've tried my best to recreate it, the key concept here is that opposite charges attract and like charges repel. So if I have a radioactive substance in my lead box here, and I allow it to travel through charged plates, how would each of the three particles travel through the plate? So let's say I had a beta particle. Beta particles are negative. Negative would be attracted to positive, so I would expect a beta particle to travel up towards the positive beta particle. Positrons are positive. I would expect positive to travel towards the negative side. Alpha particles, also positive. I would expect them to travel towards a negative pole. Gamma rays are neutral. So they're just going to go straight through gamma rays. Okay, so what do you need to know how to do here when all is said and done? You need to know how to write a nuclear equation. So we are going to go back to that example of the Ra-226 isotope. I'm going to give you your first reference table clue here. Table O is a list of symbols used in nuclear chemistry. So what an alpha particle looks like, what a beta particle looks like, what gamma radiation would be written as, neutrons and protons, which is helpful but we don't need yet, and what a positron particle looks like. So let's say I want to write a balanced nuclear equation for the alpha decay of Ra-226. Well, I'm going to start with this, and I'm going to write it in isotopic notation. The symbol is Ra. The mass is 226. How do I know the atomic number? I go to the periodic table. Ra is down here. Its atomic number is 88. So step one, I have written the isotope that is going to be unstable and is going to decay. Next, I want to see what it's going to become. All I know so far is that it undergoes alpha decay. So what that means is it spits out alpha particles. There's two ways to write an alpha particle. 4,2 He for helium or 4,2 A alpha symbol. It makes no difference which one you choose. 4,2 He. I'm not done yet because I don't know what new particle this is going to form. So what this means is my original isotope is going to lose 4 from its mass and 2 from its atomic number. I'm going to write a plus sign because this isotope is going to decay into this plus something new. And it's my job to figure out what that something new is. So what plus 4, or 226 minus 4, is going to give us the mass number of our new element, which has a mass now of 222. How do I know? Because 226 minus 4 is 222. I'm also going to lose 2 from my atomic number. 88 minus 2 is 86. How do I know which element I have now made? It's all in this 86 atomic number. On the periodic table, the element with an atomic number of 86 is radon, Rn. And voila, I have written a balanced nuclear equation for the alpha decay of radon-226. Start with this isotope. I spit out an alpha particle, which now creates this new isotope. All right, so more reference table tricks and more examples. I told you in this example that it was alpha decay. I didn't have to tell you that because all of the isotopes we're going to use are listed on table N. Table N tells you what's called the nuclide, which just means what isotope are you talking about. Don't worry about half-life until next week. But what the decay mode will tell you is which particle, alpha, beta, or positron, is getting spit out as it decays over time. It also gives you the name of the nuclide in case you need that. So for example, I might ask you a question, what is the decay mode of potassium 37? I find potassium 37, K37, or I could look up potassium 37, and the decay mode is B+, which is positron decay. How do I know that B+ is positron? Table O. So what that means is that potassium 37 is an isotope that spits out positron particles. We can use this information to write nuclear equations. So I have three examples, SR90, U238, and K37. If I want to write the nuclear equation for the decay of SR90, the first thing I want to do is write that isotope in isotopic notation and draw my arrow. 90 is the mass, and I need to go to my periodic table to find the atomic number of SR. SR is right here. Its atomic number is 38, so I will fill that in. Next, I need to know what kind of particle it spits out. SR90, if I erase this for you, is right here on table N, and it looks like it spits out beta particles. What does a beta particle look like? I go to table O, and I can write it either of these two ways. 0, -1. I'll use B this time for beta. You could have written E, it doesn't matter. Now, beta particles are a little tricky because they're negative. So what happens is, remember with beta, the atomic number increases by 1. So whatever I create here, it's losing nothing from the mass, so its mass will stay 90, but 38 was the original atomic number. So if I'm looking for the atomic number of my new element here, it's going to be 1 greater than that. So 39 is my new atomic number. Another way to look at that is by saying, okay, 39 and -1 gives me 38. To get my symbol, I go back to the periodic table and I find element 39, Y, and my new symbol is Y for yttrium. Let's try U238. First step, write the isotope symbol. I need the atomic number for uranium. I'm going to go to the periodic table. It's way down here in the actinide series. Its atomic number is 92. Draw my arrow. Next, I need to go to table N. Erase this for you. And find what particle it spits out. So U238 is all the way down at the bottom, and it spits out an alpha particle. How do I write an alpha particle? One of these two symbols. Makes no difference, so this time, just to mix it up, I'll write an alpha symbol. You could have written HE. My last step is to figure out what new isotope it would form. 238 minus 4. My new mass is 234. As far as an atomic number, 92, I'm losing 2 from that. My new atomic number would be 90. And my last step, what is element 90? TH, which I believe is thorium. and I'm done with that decay equation. Last example that we'll do together, K37. I need the atomic number for K, which is 19. I've already looked up that it undergoes positron decay from our first question. So the positron symbol is down at the bottom of table O. 0 plus 1, you can write E or B for beta. I'll use E this time. And then figure out what's the new isotope that you created. Well, 19, I'm losing 1, and my new atomic number would be 18. 37, 0, my mass doesn't change. So now I just have to figure out what is element 18 on my periodic table, and it is Ar, argon. So that's how you write a nuclear equation using your reference table. Again, I'm aware that this is confusing. So when you're writing a nuclear equation, you basically want to make sure that the numbers on the bottom and the top of your isotopes balance on both sides of the arrow. So if I were to go back here and look at my SR90 example, the top numbers on the left and right of the arrow are equal, 90, 90 plus 0. Same with my bottom numbers, 38 and 39 minus 1. 238 on the left, 234 and 4 on the right. 92 on the left, 90 and 90 plus 2 on the right. 37 on the left, 37 and 0 on the right. 19 on the left, 18 plus 1 is 19 on the right. To determine what particle is missing, you fill in your mass and your atomic number, and then you just head to the periodic table to get the symbol. I'm going to have you pause and try to write the nuclear equations for these three using your reference table, and then I will do them with you. So pause the video, give them a try. Now you're probably unpaused. Hopefully you've given them a try. Carbon 14, neon 19, and francium 220. Neon has an atomic number of 10. And francium has an atomic number of 87. So check that you've started your equations correctly. Next step would be figuring out what decay mode they undergo. I'm going to clean this up a little bit for you. Carbon 14 is beta decay, which is 0, -1, E or B. Neon 19 is positron decay, E or B. And francium is alpha. And then the last thing you'd have to do is fill in your missing particle. 14, 0 mass, 14. New atomic number 7. Nitrogen is element 7. Carbon 14 decay is complete. For neon 19, 19, 0 change in the mass, so 19 is my mass number. +1, be 9. Then I head to the periodic table, and element 9 is fluorine. And that is the decay of neon 19. For francium 220, my new mass will be 4 less than 220, 216. 87 minus 2, new atomic number is 85. Periodic table tells me that element 85 is AT. Okay. Outside of decay, there are other nuclear equations that you may be asked to find the missing particle for. It's common for loose neutrons to hit other nuclei and cause nuclear reactions. So on table E, a neutron particle looks like this: 1 for the mass, 0 for the charge, N for the symbol neutron. This graphic that you see going on the right shows an example of what that might look like. So if your neutron hits a uranium-235 atom and splits it apart, it could result in new particles as well and more neutrons. So you're literally changing the nucleus of uranium into two smaller nuclei of potassium and barium. So an equation for this might look something like what you see here. I have two examples. Same basic idea. The mass is the top number, the atomic number is the bottom number, and on either side of the arrow, they have to be the same. So what would be the missing particle in the first example? So Be9, 4, and some missing particle create two new particles, Li, 3, and an alpha particle. So what's the missing particle here? I have to figure out, okay, the masses have to add up. On this side of the arrow, the masses are 6 plus 4, which is 10. On this side of the arrow, I only have 9. So my missing mass has to be 1. And then as for my atomic number, on this side, I have a 4. And on this side, I have a 3 and a 2. So 3 and 2 is 5. So this is, again, a 1. And then I can look at table O, which is here, and that missing particle is a proton, 11H or 11P. You can write H or P. In the second example, you have cobalt 5927 forming a neutron and a missing particle. On the left, my mass is 59, and on the right, it's only 1. So what's missing from my mass on the right is 58. 27 is the atomic number on the left, and 0 on the right, so 27. And 27 is cobalt. So that would be my missing particle in this equation. So again, these rules for writing a nuclear equation: bottom numbers need to be the same on both sides of the arrow, top number needs to be the same on both sides of the arrow. Okay. Independently, you are going to complete questions 1 through 15. You're going to check them with the answer key and correct them either now or later. You're going to send me a photo of the corrected responses. And today at Zoom, we're going to be doing the even numbers together. So if you want to hold off and wait, I have one more set of notes to get through. All right, so definition time. A transmutation is a nuclear reaction where you change the nucleus of an atom. That's what we've been doing. We're changing one element into another. That is called a transmutation. There are two types of transmutations. Natural transmutations are what we just discussed: alpha, beta, and positron decay. And they usually only have one reactant, so a single nucleus undergoing decay. So that means with a natural transmutation, you only have one thing on the left side of the arrow. An artificial mutation is when you bombard the nucleus with a particle like a neutron, and there's usually 2 or more reactants. So that might look something like this: more than one thing on the left side of the arrow. Those are pretty easy to spot. So here's a question from a Regents. Which nuclear equation would be natural transmutation? Choice 1, I see 2 reactants. Choice 2, I see 2 reactants. Choice 3, I see 2 reactants. And choice 4, I see a single reactant. Natural transmutations have a single nucleus undergoing decay. Therefore, choice 4 is my natural. By default, choices 1 through 3 would be considered artificial. So you'll have a couple of those left, numbers 16 through 23. Same as before, you can add those on to your independent practice, numbers 1 through 15. Okay, so that's it for notes. You are doing basically 23 questions, and we're going to do half of them together on Zoom today if you want to tune in. What are your choice activities? I'm going to bring you over to Schoology. To show you exactly what you need to do this week. So you're already watching this lesson. You're going to complete the independent practice from the review book up to number 23. And then once I go into this folder, my next and final task is to access the choice activities folder. What you'll find in here this week is, if you don't have a review book, here is the scan of topic 12. Once you do your questions, the answer key is here. And then in the choice activity folder, I'm going to have you research a nuclear scientist. So this is your choice for this week, is you can select any nuclear scientist. You're going to answer 10 questions as if that is how he or she would have answered them if you had interviewed them. So say you select Niels Bohr. Number 1, what is your name? Niels Bohr. During what time period did most of your contributions occur? You would do some research there. You're going to physically submit this form, and if you want to change up the form in any way, as long as you answer all 10 questions about that scientist, you will be good to go. So I've also given you some websites to set you off in the right direction there. So this week, there is no quiz. You are going to submit your corrected responses from the review book, and you're going to submit the document on interviewing a scientist. So if we go back to the PowerPoint, I'll clarify that even further. So this week, what do you need to submit? You need to submit the corrected review book questions 1 through 23 from topic 12. You also need to submit your interview sheet based on the nuclear scientist that you researched. I have no problem with you sending them together as one document, but each one will be counted separately for a grade. So you'll get a completion grade for the review book questions, and you'll get a completion grade for your interview sheet, but you're welcome to send them together. Your choice this week is, well, you get to choose which scientists that you researched to interview, and then you can decide whether you want to do the review book questions on Zoom, or you can do them independently. The Zoom today will be from 1 to 1:30, and I will send the code out 15 minutes prior. We will do all of the even numbers together, and then you'll just have to do the odds, correct them, and submit your questions. You can take a picture of it. You can send me a OneDrive document. It really makes no difference. There is no quiz this week. You will just have 2 completion grades, 1 for your corrected review book questions, and 1 for completing the interview sheet with a nuclear scientist. All right, that does it for this week. Hopefully I'll see a lot of you from 1 to 1:30. You do need to have watched this video before you join the Zoom, or you'll be pretty lost. But I know that this can be a confusing topic, so hopefully I'll see a lot of you at Zoom today, and we will do all the even numbers together. All right, the quicker you get this done today, the quicker you're done for the week. Hopefully you'll reach out if you have any questions, and I will chat with you today on Zoom from 1 to 1:30.